Hello, Anush.
Hello, Matt.
How are you?
I'm good. How are you?
I'm doing very well, thank you. So, whereabouts in the world are you at the moment?
I'm in Norway, in Oslo, the capital. Yeah, in my home office today.
Oh, fantastic! So,
Yeah.
well, really have got a full gamut of people from around the world. I'm here in Chicago, so
Nice.
it's early morning for me, or early-ish morning. Whereas, I guess for you, it's more like the same time as the conference, right?
Yeah, I think I'm 2 hours behind, so it's 4:30 in my place.
Oh gosh, right, yeah. So yeah, for me, it's 9:30 in the morning. So, but I'm really looking forward to hearing your talk today. I hear you're going to use some kind of website.
Yeah,
Um,
yeah. They said like there's going to be an expert in the talk. Like
I wonder when
I
he'll
think
turn up, or he or she will turn up. I mean, maybe.
I imagine like they're probably going to have someone who like knows a bit of C++ and maybe a bit of assembly, and maybe they've even used Compiler Explorer before. But then they
What is
put
this
on the
compiler? What? I don't know.
Compiler
It just
Explorer.
sounds.
It's also known. I think they call it like Godbolt or something.
Oh, really?
So yeah, so it's good to have, yeah, if anyone in the audience doesn't know, then Matt is actually the creator of Godbolt or the Compiler Explorer. So that was
It's
a good choice of expert, I'd say.
it's an interesting one, right? I'm certainly an expert in how the site works. I don't know if I'm an expert in everything else that goes alongside, but I'm looking forward to hearing your talk and learning a thing or two. Um, for me, the site was scratching an itch that I had, and I'm just so glad that so many other people use it for different reasons. Maybe
Yeah,
some people use it as like a little IDE, and I'm glad that you're able to bring more people to be able to understand the output of it. Or that's the hope anyway, right? Is
yeah,
that people shouldn't be scared by what they see in that right hand pane of the of the website.
yeah. So that was me. I was like, I want to use this site, and I didn't understand it, so I figured, okay, let's try to write a talk about it because then I really have to learn this stuff. So
Oh,
that's
the old, yeah, yeah. You don't really know something until you try to teach it to somebody else.
yeah. Actually, just earlier today, I was watching your the bits between the bits thing from CPPCon a few years ago. I
Yeah,
think you mentioned it was just like the same thing. Like, here's GDB. Like, let's figure out what's going on. Uh,
that's
yeah,
That's exactly
good.
how that went down. Yeah, that
Yeah,
was very much me, sort of like going, well, I know a little bit about this, and actually the process is interesting. I thought is like describing that I didn't just know all this stuff, but like you could dig around, and this is how you dig around to find this kind of stuff. But
yeah,
yeah,
yeah, absolutely. Those are fun talks to make when you like. It's a lot of work, but it's fun when you learn a lot when you do it. Also,
absolutely, it's really nice to have to learn and then have something tangible to show for it at the end of it, be it like a
yeah.
little program that you've written or a presentation that you've given to give other people an insight into what it is that you've been up to and doing. So.
Yeah, and then you figure out all the things you got wrong because you actually try to explain it. Like, oh, well, this can't be right. So yeah,
Exactly. Yeah, that's
great
very
way to
much how
learn.
it goes.
Yeah.
So I think we're waiting a couple more minutes just to make sure that everyone's here and ready to watch your presentation. And so, when you're not writing C++ or staring at assembly code or whatever, what kind of stuff do you do outside of the the sort of tech world?
Well, it's kind of tech as well. I am into like industrial and EBM music, so basically noisy, angry synthesizer music.
Oh my
And
gosh. I had no idea. That's awesome. That's yeah.
yeah,
What sort of? I mean, I think like Nine Inch Nails kind of stuff, or is that kind of thing with the big steam
yeah,
press industrial drum stuff? Or
yeah, kind of like Nine Inch Nails without the guitars, kind of. So
okay,
like more electronic side of it. So
um, very interesting. Oh gosh, we should talk more after this. Then that's definitely my kind of cover. That's definitely good working music, right? Lots of
yeah,
silly noises, loud pumping.
yeah,
At least for me, anyway.
yeah,
That's cool. Um, yeah, and I know
yeah,
that you run a couple of other websites yourself, right? You're not.
yeah. Yeah, so I have this cppquiz.org, C++ quiz site, and yeah, I'm on Twitter quite a lot as well, like hang out and just chat and yeah, post about silly stuff. I have a slide on it later in the talk, so
Oh, fantastic! So we'll
mention it
get to
there.
see what the other stuff that you do. Just checking, making sure. I think we're all right, nearly on time. We've got a few more moments to talk about bits and pieces. Uh, I learned today that one of those Twitter accounts you talk about. Maybe you have got a slide about this. So I don't want to give away
Oh,
too
just go
much.
ahead, guys. It's not.
Ah, all right, yeah, one of those the effective CPP or account, which is a
Yes.
source of much amusement to me and many other people. Is your brainchild?
Yeah. So it's basically a place where I post things that look like proper C++ advice, but it's just spectacularly wrong in some sense.
That's
So
great.
I started like putting out some tweets, and then like people started tweeting to me and like mentioning me every time they should post about some C++ stuff, and then it's kind of turned into like an aggregator of stupid C++
The worst
things.
kind of C++ advice, which is to
Yeah,
say quite a lot of C++ advice.
yeah.
Anyway,
So
well,
sort
I
of like
think
yeah.
we're
Okay,
about at time,
yeah,
so I think we should get this show on the road. So
right.
let me say a few things, and so for those who've just joined us, hopefully you're in the right place. This talk is by Anush Knatten, and I hope that I've been practicing saying this, so I've got something roughly right.
Yes, very good.
Anush started programming in Turbo Pascal in 1995. Gosh, those were the days. And he's been programming professionally since then. He's currently a senior developer at Zivid, where he makes 3D cameras for robot vision. So when the robot overlords come and get us, you can blame him for giving them the power of sight. He's
Yes,
the author of CPP Quiz. Yeah, sorry, you were going to say?
yeah. And I was just saying, I will tell them like when they come for us, I'll say, hey, I made your eyes. Don't
That's
shoot
right.
me.
Yeah. Maybe they'll save you. Yeah,
Yeah,
you'll be one of the few remaining when spared by the robots.
that's my plan.
Yeah, he's the author of CPP Quiz and the blog C++ on a Friday. When he's not writing seriously about C++, he gives terrible advice on Twitter at Affected C++. And when not giving terrible C++ advice, he likes to make industrial music, as we were just learning, with his band Modulo 1 and go on festivals with aggressive Germans and noisy synths. Is the aggressive Germans and noisy synths, or aggressive German noisy synths? Or
You can mix those words in any order, really.
they all work in any order. Well,
Yeah.
anyway, it's lovely to have you here. Really looking forward to your talk. Take it away, my friend.
Right. As you just heard, my name is Anders, and welcome to Just Enough Assembly for Compiler Explorer. Yeah, as Matt said, also I work in Civid in Norway, where we make these cool eyes for robots, and yeah, I'm mostly focused on C++ there these days. And we are hiring, so if this sounds cool, hit me up on Twitter or Telegram or something. And yeah, here's the C++ quiz site that Matt also mentioned. So it's a bunch of C++ questions. It's like main programs, and you have to figure out what the output is going to be. And there's always some trick to it. And yeah, I also hang out on Twitter quite a bit. So Knatten, that's my main account. And then I have one account for CPP quiz, and then for all the terrible C++ advice on effective CPP. But we're not here to talk about any of that. We're here to talk about Compiler Explorer. And for any of you who haven't used Compiler Explorer, it's a really nice site where you can just paste your C++ or C or whatever language on one side of the site, and then on the other side, you can see the assembly output. And why would you want to look at the assembly output? That's because you write your C++ or whatever for other humans to read, right? And then the compiler will translate that into something that runs on the CPU. And that something is machine code. And for every machine code instruction, there's a corresponding assembly instruction. So if you can read the assembly instructions, then you can know what the compiler actually decided to tell the CPU to do. And that can be really interesting. And you can also try out different compilers. You can try out different compiler options and see how that affects everything. And it's really a convenient thing to do. So let's just have a quick look at the site. So this is how it looks. I just pasted some random code here to the left. Don't worry about the code itself. It's not really interesting. Just for the example. And you can see I get all the assembly code here to the right. And you can see that it's, here I have used GCC 11.2, but there's like a whole range of compilers here you can choose from. And here you can put in different compiler options, and then you can see the assembly here. And you can see it's been syntax highlighted. And when I move my cursor around here, you can see that it highlights the C++ code or C code and the other way around. So you can see like the correspondence between the C code and the assembly code. And to the right here, you can see it's quite a lot of stuff going on. But in 50 minutes or so, we are going to understand everything that is on the right-hand side here. We're going to understand what it means, and we are also going to understand why all of that code is there. So what is it doing, and why did the compiler choose to emit that talk? That code. And That's not going to be because I'm going to go fast. I'm going to go really slowly and build up from the very fundamentals so that we have like a basic understanding of how this all works. So if you see here, we're probably gonna have to learn a lot about these d-word putter things, and there's a bunch of move that seems important, and this RBP thing, and there's lots of stuff to learn. So let's go back to the slides and start looking at this. So if you have any questions during the talk, I have Telegram open here on the side. So if you're on the Telegram channel, you can post any questions there about the slides. If you have a question about like how does this work, or I missed this detail, can you explain a bit more? And then I'll try to explain as we go, because it's easier to do that when the code is up here and before we start moving too far along. And then at the end of the talk, there will be a lot of opportunity to ask like bigger questions after. And yeah, today, most of the slides are in this like toy slideware emulator kind of thing. And in the middle, we'll always have a view into the CPU. And inside of the CPU, there's a bunch of registers. And really, to be able to do anything interesting with any data, you have to get it into those registers in the CPU first. And for each example, I'm going to visualize only the registers that are relevant to that example. So there are a bunch of registers. And in this first example here, we're just looking at RDI and RSI, just two arbitrary ones that I picked to use in this example. We can see that we have the contents of the register here. I'm displaying it in hex because that's just the most convenient way to look at stuff, and have the register name to the left. And one important detail is that at the beginning of each example, the register is going to be initialized to 0, and that does not happen in reality. So in reality, the register just has whatever was in there from before. But just to make the examples easier to follow, they are 0 initialized at the beginning of the example. And that's for the intro. Let's get some assembly code up. So here we have some assembly code to the left. And assembly is a very simple language. It's not easy, but it's at least simple. So we have every line is one instruction. So you start with the instruction name to the left, and then you have 0 or more operands. And then, yeah, one instruction per line, basically. And in this little toy emulator thing, I've also put up this orange step debugger indicator. So we can step through a program like this, and then we can see what happens to the registers and later also to memory. So let's start with the first instruction. It's a move instruction. And just like in C++, in assembly, move does not mean move. So in assembly, move happens to mean copy. So move RDI 2 means to copy RDI and 2 in some way. And then the question is which one gets copied to which. And I'm using the Intel assembly syntax here. It's the one I personally prefer. It seems to be the most popular these days, and it's the default one on Compiler Explorer. So that's the one I use. And in the Intel syntax, you have the source to the right and the destination to the left. So move RDI2 means copy the value 2 into the register called RDI. So if we execute that instruction, we can see that RDI now holds the value 2. Then we can do move RSI 4, so we get the value of 4 into the register called RSI. And then the next instruction is an add instruction, and that does, in fact, add the two numbers. So it's going to add the contents of RDI to the contents of RSI. But where does the result go? Because like in normal mainstream languages, we typically go like auto result equals x plus y or something. In assembly, the result goes in the first operand. So we're going to add RDI to RSI and then store the result in RDI. So 2 plus 4 equals 6. If we execute this, we get the value 6 in RDI. Right? If there's any questions so far, then just post them on Telegram. Yeah, but we have a tiny amount of small registers inside the CPU. So if you're going to actually do something useful, we are going to need to have some memory as well. And in this talk, I'm only going to be talking about the stack, but we are going to talk a lot about general forms of memory addressing. I will just happen to be using the stack, but anything I say about general memory addressing is also true for the heap or for global data or anything like that. So I have drawn up here a bunch of memory locations. We have like 1 byte on each line over here. And you can see the contents. And then to the left, you have the memory address. And memory addresses will, of course, be 64 bits. This, maybe I forgot to say, this is about X86 64 assembly. And so, yeah, 64 bits addresses, but I've just truncated them because I don't want to have too much noise on the slides. And you can see that you have a higher addresses at the top here, so B3, B2, B1, B0. So we have lower addresses at the bottom, higher addresses at the top. And on X86 64, the stack grows downwards like this. So the stack is here, and then it grows downwards like this. I've also introduced one more register here called the RSP, which is the stack pointer. So the stack pointer is a register inside of the CPU, which always points to the current top of the stack. And just for convenience, I'm also visualizing that over here with this little RSP pointer, which points to the current top of the stack. So someone was doing something on the CPU and the stack, and now we are in our part, and they will have then left the stack pointer here. So now, from here on, it's our stack, right, that we can use. And when we do use the stack, it's going to keep growing downwards like this. So first thing I want to do is to just put some number in a register. And the first instruction here, move RDI and this long number, just so we can have a number that fills the entire 64-bit register. And then I'm going to do push RDI. I'm going to push this onto the stack. And the question then is, how many bytes do we need to put onto the stack? Well, it's a 64-bit register, so it's 8 bytes. So we're going to take these 8 bytes here on the stack and get the number in there. And the only remaining question then is, like, what is the value of this byte and what is the value of this byte? So that could, like, where does the 10 go and where does the FE go? And the answer is that on X86 64, this is a little endian architecture. So the least significant byte of any multi-byte number will go on the lowest memory address. So when we execute this line, we see that we got all of our DI over in memory here, and the least significant byte is at the lowest memory address. Then we can also pop. So and yeah, when I did the push, I only specified the register name. I don't say like how many bytes to push, where to push it or anything. It knows it's a 64-bit register, so it's going to push 8 bytes, and it just goes on the top of the stack. And the same when I go pop RSI, it's going to pop, since RSI is 64 bits, it's going to pop 8 bytes off the stack. So when I do that, I get those bytes from the stack into RSI, which was the operand to pop here. And you can see also that RSP has now moved back to where it was before I pushed onto the stack. So that's how you push and pop values on and off the stack. But yeah, then just pushing and popping stuff on the stack isn't that really that useful. You can like do some simple stack machine things, but what you really want to do is to have this random access memory. So we want to be able to randomly access it, or at least arbitrarily access it. So let's look into how you do that. And first, we need some values in some registers again. So I'll just put a bunch of 3s in RSI, a bunch of 2s in RDI, and then we're going to do another move instruction. And it's still exactly the same as before. So we have this move instruction, and then we have 2 operands. We have this one and this one. So the second operand is RSI, so that's familiar. We're going to take whatever is in RSI and put it somewhere. And where are we going to put it? We're going to put it in keyword putter RSP -8, right? What does that mean? Well, keyword means quad word. So a single byte is a byte. 16 bits is a word, 32 bits is a double word, and 64 bits is a quad word. So keyword is short for quad word, which means basically 8 bytes or 64 bits. And keyword putter means that you want to dereference an address. So when I want to put the value of RSI somewhere, I'm going to put it into RSP -8. So I'll go RSP -8, that's down here. And RSP -8, that's A8. And then I just dereference this value A8 with a keyword putter, so I know where to put our RSI. So I take the value of RSI, which is a bunch of 3s, and put it into here. RSP minus 8. And this is actually how a variable looks like. So if you had gone in your C++ code and you went long L in your, like as a local variable in a function, then this is how that would look like on the stack. And you can also use memory in other instructions than move. So you can also add from memory. So we say again here, add RDI. So we're going to add something to RDI. What are we going to add to it? Well, keyword footer RSP minus 8 again. So RSP minus 8, and then dereference that, get the value out. So we take all the 2s here in RDI, add all the 3s here from memory, and we get a bunch of 5s in RDI. Just as I said on the previous slide, assembly will leave the result in the first operand. Right, then we know how to both read and write from local variables. So before I continue, I just want to go briefly over register sizes. So in the beginning, when they introduced the x86 architecture, all the registers were 16 bits. So we had like AX, BX, CX, DX, and stuff like that. And then often you just want to use a single byte. So they have these aliases like AH and AL for the high and low parts of the AX register. So it's the same register. So if you write to AL, it's just like the lower half of AX. And if you write to AH, it's just the higher part of AX. So it's just one register, just like you use into that register. And then the 386 came along, and we got 32 bits numbers. Then we got the E for the extended register. And still, all of these are just views into the lower part of EAX. And then finally, we got the x86 64. We got the R version, so RAX, RBX, etc. And still, all of these are just views into those. So it's just one register with many names for the various parts of it. And as mentioned, I like quizzes. So the first quiz question that you'll just have to solve yourself, since this is not really that interactive, is how big is an int? And we are on a 64-bit architecture, so the answer is 32. When I went from 32-bit to 64 bits, they didn't want to change the size of all the ints. It would like double the size of everything, and it would be super surprising if your code suddenly started having differently sized ints. So the int is still 32 bits. So here in the 64-bit registers, you can put signed or unsigned longs. In the 32-bit ones, you can do signed or unsigned ints, 16 bits, signed or unsigned shorts, and in these ones, you can put signed or unsigned or just plain chars. That's for the x86 64, but really it's up to the implementation. So on other platforms, you can have smaller or bigger ints if you want, and it's still going to be conforming to the C++ standard. Right, so let's do one example with a smaller part of the register. Let's do ESI and EDI here, and now we're doing 32 bits, and we're doing like regular ints, basically the most common data type of them all, I would say. So we're going to do exactly the same example as the previous one, but we're going to use 32-bit ints instead of 64-bit values. Registers are now called ESI and EDI. You can see here we're still visualizing the full RSI and RDI. And then we can see when you put all these 3s into ESI, they get written to the lower half here of RSI. And then we can put a bunch of 2s in EDI. And then we see this move thing again, where we're going to move something into memory. And this time we go D-word putter, which is a double word pointer, because now we're talking about 32-bit values. So we're going to take this 4 bytes here from ESI, and then I just happen to decide, well, I'm going to put them at RSP minus 4. This expression here could really be anything, but I just decided I want them here, over here. So RSP minus 4, dereference that and put ESI into that. So we get all of those 3s into memory. And again, we can also add. So we're going to add D-word putter RSP minus 4, which is the same location in memory that we just saw. Add it to EDI, and as always, you get the result in the first operand. So we get like all these 3s added to all these 2s, and that's also where the result ends up with all these 5s over here. So now we can write and read ints as well. But writing and reading single ints and longs, that's not really enough. We also want to work with more data. So we want a lot of stuff, but right now what we want is arrays. And arrays is also a very convenient way to talk about some more interesting assembly code as well. So I'll just start by putting some values in memory. And this time I'll just use 16-bit values. So now we say word putter, and you can see I'm only using 2 bytes for these values. So at RSP -8, 6, 4, and 2, I'm going to put these values. So I'll just execute those 4 lines. And we can see that we got these values over here in memory. But these are just bytes. Assembly doesn't have any types. Assembly doesn't care. These are just bytes in memory somewhere. And it's up to us really how we want to interpret these. So these could be 8 separate bytes. It could be like 1 long. It could be part of a network packet or an employee record. It could be whatever, right? It doesn't. There's no types. So in this example, we want to treat these 8 bytes as an array of 4 shorts. So 1, 2, 3, and 4 values in this little array that we have here in memory. And in C and C++, we're used to arrays being basically almost pointers, right? Every time you want to do something with an array, you just have a pointer to the first element. So that's what we're going to need. We're going to need a pointer to the first element. And just for this example, I decided I want to use RDI. I want to point that to the first element of the array. And the first element is down here at A8. So to put that address into RDI, I'm going to use an instruction called LEA, which stands for load effective address. And what that does, it's going to compute this address in here, just like we saw with these memory addressing schemes before. But instead of dereferencing it and getting the value out, I'm going to get the address out. So RSP -8 is A8. And then I'm going to use the value A8 instead of using the value which lives at A8, which is 11, right? So this is going to take A8 and load that address into the register called RDI. So if I do that, I get A8 in RDI. So now RDI is a pointer to the beginning of my array. And then let's say I want to get at the 4th, or if it's like 0-based indexing, the 3rd element of the array. And to do that, I have to skip over the first 3 elements times their size, right? So I'm going to move into AX here, something that lives at RDI plus 6, because this is the beginning of the array, and I have to skip over these 6 bytes to get at the last element in the array. Yes, we do RDI plus 6, dereference it with a word putter, 16-bit value, and move that into AX. So we got these 4s from here into the register RAX here. But we don't really want to hard code. This isn't even the index. Like, it's the actual the byte count into the array. We don't want to hard code that in our program, right? We want to be able to have a parameterized way of having an index somewhere. So let's say we will want to put our index in RSI. So we're going to use this as the index. So RDI is going to be the pointer to the beginning of the array, and then RSI is going to be our index that we're going to look at. So let's say we want to get at the 0th element. We put 0 in RSI. And then we can do something more interesting, because then we can say, well, we want the RSIth element. And since each element is 2, we have to move 2 bytes long. We're going to multiply it by 2. And then we add that to the base pointer of the array. So we have RDI pointing to the beginning, and then RSI times 2. So that's 0, since RSI is 0. And we get at RDI, which is pointing at A8 here. RDI is pointing here, plus 0, so that's A8 here. And then we move that into AX. So now we got our 1s in AX. And then the really nice thing happens, because then we can increment our index with the inc instruction, which just increments its operand. So inc RSI. RSI goes then from 0 to 1. And now we can use exactly the same instruction here. This is byte for byte, the same instruction as this one, to get at some other data. Because now everything is parameterized. Both the base and the index has been parameterized out of the instruction, which is really convenient. And that seems like something that we would want to use in like more general code, like in a loop or in like some sort of control flow. So that's what we're going to do as well. We're going to go to control flow. Yeah, so the first control flow we're going to look at is if. And in this tiny example, we're going to want to compare two numbers, and we're going to see if the first number was bigger than the second, then we're going to return true. Otherwise, we're going to return false. So let's see how we're going to do that in assembly. So first, let's put some numbers in registers again. So put 3 and 2 in RDI and RSI. And in assembly, we don't have any nice if and else constructs or anything like that. We have basically comparisons and goto. And goto is considered great, right? So that means we can basically do anything here. The first thing we're going to do is to actually do the comparison of the numbers. So I'm going to do CMP for compare, RDI and RSI. And nothing happened when I did that. And that's because compare doesn't really return any values. It doesn't really do anything. It just compares the numbers and then stores off a bunch of metadata in some flags inside of the CPU. And then on the next line, we can do a conditional jump. So the one we're going to do here is called JG, which stands for jump if greater. So if the first operand to the previous comparison we did, if the first operand was greater, then we jump. So JG goes and then looks at this metadata that CMP stored away somewhere in some flags. If it was greater, we are going to jump to a label. And that label, we just named it greater because that's a convenient label for it. So we just jump down here. And then we put 1 into RAX because we're going to have 1 representing true. And we'll have RAX be our result register. So we're just going to store the result here. So we jump down here, put 1 into RAX because, well, it was true. The first number was bigger than the second one. What if it was the other way around? So the same example again, but this time we're putting 2 and 3 instead of 3 and 2. So this time when we do compare RDI and RSI, this time RDI is not bigger than RSI. So we just evaluate the CMP instruction. Nothing happens that we can really see. And then we do jump if greater. 2 is not greater than 3. So when JG goes and looks at the CMP result, it finds, well, it wasn't greater. Then we just fall through to the next instruction. The next instruction says move RAX 0, and that's because 0 is what we're going to use to represent false. Put it in our result register called RAX. And we're done. But there's one more thing we really have to do. We have to have an unconditional jump here, because if we now just didn't have this one, we would have just fallen through into the other part of the if statement and then overwritten it by the true value. So we need to do an unconditional jump to jump like outside of the entire if thing and get to the end. So if you're familiar with C and C++, then you're typically used to have like the if thing on top and the else thing at the bottom. But in assembly, it's often the other way around, that you get like the else thing on the top and the if thing at the bottom. This sometimes. So that's something to be aware of. Right, so here are a bunch of different ways of jumping around with the conditional jumps. First, you always do a CMP, or not always, but yeah, that's one way to do it. You do CMP and with 2 operands, and then you get the metadata stored away somewhere. And then you can jump if they're equal, we jump equal, jump if they're not equal, jump if the first one was less or equal, greater, or equal. And as I said before, assembly doesn't have any type. So assembly doesn't know, like, these bytes that are over here, are they supposed to mean like a signed number or an unsigned number? And that is important when you're going to compare a bunch of bytes, like what do they mean? Because if you have like a really large unsigned number, it's going to have a 1 at the beginning. And if you have a negative signed number, it's going to have also a 1 at the beginning and look like a really large unsigned number, right? So we have different instructions for comparing or doing conditional jumps with signed or unsigned numbers. So these are for the signed numbers, L less and greater, and then like the names less and greater are taken. So for unsigned ones, we get below or equal, above, and above or equal. And the way this all works is that CMP is basically just kind of a subtraction operand. It's just subtracting the second operand from the first. And if a subtraction operation results in 0, then the 0 flag gets set. So if I want to jump if equal, I can just check what's the 0 flag set. And jump not equal, I can just check the same thing. And if operand 2 was greater than operand 1, when you subtract operand 2 from operand 1, you're going to get a negative number, and then the sign bit gets set. And then if I want to check, then if the second one was less, I can just check, well, was the sign bit set or the 0 bit set? And if neither of those, then it was less. So that's how that works. And then we have variables, we have arrays, we have memory addressing, we have conditionals, and then we need loops. And assembly, as I said, doesn't have any nice if and else things, and of course it doesn't have do and for or while or anything like that either. But we still have our good old comparisons and our go-tos, so we can do loops as well. So let's implement a little loop here. And we'll use RCX as the loop counter. So I'll start my loop at 1. So I'll do move RCX1. Get 1 in here. And I'm going to accumulate some results in RAX. So I'll put 0 into RAX just to zero it out before we start. And then I want to loop. So the loop counter is now 1. I want to loop until it's 3. So I'll compare RCX, the loop counter, with 3 to see if we have reached the end of the loop. We have not. So then we compare those, and then we jump if equal. So is RCX 3? No, it's not. So then we do not jump if equal. We just fall through to the next one. And just to have something to do in the loop body, I just decided I'm going to accumulate all the loop counters into RAX. So I'll just add RCX to RAX just to have some arbitrary random thing to do in the loop body. Then I'm going to do inc RCX to increment RCX, the counter, which is at 1. And now if I increment it, it's now 2, right? And then I just jump back to the beginning of the for loop again. Then I again check, is it RCX equal to 3? It's not, so we don't jump, we just fall through here. We keep adding RCX to RAX. We increment RCX, jump to the beginning of the for loop. Are we 3 yet? Yes, this time we have reached the end of the loop. So then we jump to end for that label at the end of the loop, and the loop is done. So now we have loops as well. And yeah, if you want to see how that would look like in C or C++, we can do int RAX equals 0. That's this line here. For int RCX equals 1, so that's this one. RCX not equal to 3, so that's this comparison and the jump if equal together. And then we have plus plus RCX, which is this inc RCX. And then we have this RAX plus equals RCX, which is this add here in the loop body. And then we have this jump here, which is like basically the curly brace thing where you jump back to the beginning of the loop. Yeah, again, if you have any questions, just please post them on the Telegram chat if you're there. Otherwise, we can do them after the talk. Right, so let's have a real example here. And I will switch to my browser and have a look at Compiler Explorer. And here's a very simple example. I want to introduce functions now. So we have this simple sum function. It takes a and b and returns a plus b. So it's a super simple function. Sum of int a and int b return a plus b. And here's the assembly code for that. And I just went and copied that into this little toy slideware emulator thing. And let's see how that looks. So I put, again, the CPU here in the middle. We're going to need a bunch of more registers this time, not because I want to, but because GCC decided these are the ones it wanted to use for this. And the first question we will have to ask ourselves is, like, someone called this function. Someone had to pass a and b, the arguments that we're going to add together. And how do they get that info into our function? And the way they do it is dictated by the calling convention. So on any system, you'll have a calling convention. I wrote this talk on Linux, which uses the systemv AMD64 calling convention. I think that's what's being used on the Mac as well, which I'm presenting on right now. It's used on most Unixes. And Microsoft has a very similar calling convention. But the calling convention specifies how do you get stuff in and out of functions. And one thing it says is, if you're just going to pass a few ints, just leave them in some specific registers. So whoever was calling this function was probably already working with this data. It had this data in some registers. So it's super nice to be able to just leave those values in the registers and then just call our function. So you don't have to push them on the stack or copy it to memory or something like that. Just leave them in these registers, transfer control to us, and we can just keep running with the values in the registers already. So that's a really fast way to get data in a function. So we can see here that whoever called us has put 2 and 3 for A and B into the registers RDI and RSI, which are the first 2 registers to use for passing into functions on my system, on Linux. And then we can start looking at the assembly code here. So what's going on? The first instruction we see is push RBP. And that's, again, due to the calling convention, because the calling convention says there are some registers that if you mess with these registers, you have to restore them before you return to whoever called you, because they were probably using these registers for something. So whoever called the sum function, they were probably using RBP for something. So let's make sure we're able to restore it. So we're going to push it at the beginning, and we're going to pop it at the end of our function, so that when we're done, in case we messed up RBP, it's going to be restored to whatever it was before we were called. So let's just push RBP, and we can see that the stack pointer was bumped down here, and the previous value of RBP is now in here. I just have zeros. It probably had some actual value, which will now be in here. And it seems like it was a good idea to save RBP, because the next instruction says move RBP RSP. So we're going to copy the value from RSP into RBP, and we're going to overwrite RBP. So it was a good thing that we took a copy of it. And why do we take this? Why do we copy RSP into RBP? Well, RSP is the stack pointer, and everything we do inside of our function is going to be happening inside of our stack frame. So everything is going to be relative to the start of our stack frame. So then it's nice to have a copy in RBP, because in our function, we might be pushing and popping stuff on the stack. We might be calling other functions, and like RSP might be jumping up and down all over the place. So if the first thing we do is to just take a copy of RSP into RBP, then we know that we have a stable base to do all our internal stack frame addressing from. So let's do that. Then we have A8, now the stack pointer, both in RSP and RBP. And we can see I'll visualize that over here as well. And in this particular example, we are not messing about with RSP. So we didn't really have to do this, but GCC just like always writes this preamble. And this is on O0. So if you do O2, then of course a lot of this stuff goes away. So then comes a bunch of more lines. And I didn't choose to write this code. GCC wrote it. I'm not sure why it did all of the things it did, but I'll explain some of it at least. The first thing it does is to take this EDI and ESI, which it's so nicely just left in the registers to be super quick. It puts them back into memory. So let's do that. It's going to put EDI into RBP -4 and ESI at RBP -8. So that's our A and B. If you execute those 2 lines, now we have our values here, A and B. And now this is like actually things in actual memory. So these are now L values. You can take their address. You can inspect them in a debugger. So it's they are now proper variables, which is nice, and which is why GCC did that. Then it's I don't think like GCC isn't thinking about exactly what to do here. It's just like going by the rules, right? To generate this very general solution, and then the optimizer is gonna just squash a lot of it away. So what it does then, it's the time to start adding this stuff. And to add it, it decided to put RBP -4, so this 2 here, into EDX, and RBP -8, this 3 here, into EAX. So let's execute those 2 lines. And we get our A and B that we got initially here in RDI and RSI, then over in memory, and then back into RAX and RDX. And and then it's time to add these numbers. So add EAX, EDX, that's going to add the 3 and the 5, and as usual, leave the result in EAX. So we add those, we get 5 in EAX here. And this is our result that we want to return. And then the question is, how does one return a value? And again, then the calling convention specifies how to do this. And our calling convention says, if you're going to return a single int, just leave it in EAX. And again, this is super fast because then when we return control to the caller, it can just start or keep working with that data already in that register. There's one more thing we have to do before we return, and that's to pop RBP so that we restore the base pointer that our caller was probably using to manage their stack frame. So we pop that and then return. And return simply just returns control to whoever called us. I think that was quite a lot of stuff going on to just add two numbers. So if you go back here to Compiler Explorer and look at our sum function and all of this stuff, let's see what happens if we do Schau. And that seems a lot nicer. That's just one instruction and return. And maybe you recognize this instruction. It's the LEA thing again, load effective address. And we're not loading any addresses. We're just adding two numbers. So what's the LEA thing doing in here? Well, first of all, remember that assembly doesn't have types. So assembly doesn't care if something is a value or an address. It's just adding bytes. That's basically what it's good at, right? And LEA is convenient because LEA allows you to specify where to store the result. So instead of just adding RDI and RSI and then moving it into EAX as a separate instruction, LEA can do this in one operation, add the two numbers and put them into EAX, which is the return register. So then, and LEA is a really fast instruction as well. It's super optimized because you're going to do it a lot. So it's a quick way to add two numbers, put it into the return register. And basically, this whole function ends up being one instruction plus a return. Let's just see. O3, O1, OS, same thing. Right, so if you go back to the slides again, now we have seen variables, memories, arrays, control flow with both if and for loops. We start looking at functions. And then I think we are ready for the holy grail of programming paradigms, which is, of course, procedural programming. So let's see what happens if we have a full function which is calling another function. So here's a slightly larger version of the previous example. So we used to have this sum function. Now we have a sum times 2 function. So we're going to take two parameters here, a and b. We'll add those together and pass it to a times 2 function. And that times 2 function is just going to multiply the argument by 2 and return it. Okay, so we'll take a and b, add them together, and then pass it to a function which multiplies it by 2, and then return that value. And now you can see we got two functions over here. So it has annotated it as well. So here's the sum times 2 function. Here's the times 2 function. So let's copy all of this into our little toy emulator again and see what happens. Right, so this is the busiest slide of the entire talk. We need some more memory here. So if you remember, the memory was coming down like this. The stack was growing down like this. And then I figured I'm going to need some more memory for this, this slide. So I just kept going here to the right with another column. So it goes A2, A1, A0, 9F, 9E. So the addresses keep growing downwards like this. So the stack is going to grow down like that. And let's see what happens when someone is calling the sum times 2 function. So they will have put their arguments into EDI and ESI again. So we can see here, EDI and ESI will have the 2 and the 3 that they wanted us to add and multiply by 2. And then let's start executing the assembly code. And first we're going to do push RBP, because remember we have to preserve RBP in case we overwrite it so we don't mess up for whoever called us. And then we take a backup of RSP into RBP, or a copy of RSP into RBP, so we have a stable pointer to the beginning of our part of the stack, our stack frame. So now we have both RSP and RBP pointing here. So this is where our stack frame starts. This is where we are free to do whatever we want. And this time it was actually convenient to take that copy of RSP into RBP, because the next instruction is sub RSP 16. So now we're going to subtract 16 from RSP. I'll go ahead and execute that. And then we can see that RSP moved all the way down here. And that is good because we are going to call another function, right? We are in the sum times 2 function now, and we are going to call the times 2 function. And then the times 2 function is going to need to use the stack. So we first bump the stack pointer here so that whenever that other function is called, then they can use that part of the stack, right? So we have this stack frame all the way over here, and then the next function can get whatever stack space they need further down here. But we now have a stable pointer to the beginning of our stack frame in RBP. So then you can see also we're using RBP relative addressing over here. And GCC, just like in the previous example, we got the 2 and the 3 here in EDI and ESI, and it decided to put those into memory. So RBP -4 and -8. So if I do those 2 instructions, we have our 2 and our 3 over here in memory again. And again, just like in the previous example, they go back into registers again. So they go into EDX and EAX. So now we have our 2 arguments in here, like 3 here and the 2 here. And then we're going to add them because sometimes 2, remember, it's going to add A plus B and then pass it to this function to multiply by 2. So we're adding EAX and EDX here. So that's 3 plus 2 equals 5. And as always, the result goes in the first register, so it goes in EAX. If we execute that, we have now the value 5 here in EAX. And now it's our turn to call another function. So this is the first time we are calling another function. And remember, the calling convention said the first int goes in RDI or EDI, for instance. So then we have to take this 5, this intermediate result that we have, and put it into EDI before we call that other function. So let's do that. Now we got the 5 into EDI here. And then we are going to call the times 2 function. And all it takes to call this function is just to say call and then the name of the function. So now control flow will just, control is going to be passed to times 2 function, which is down here. And what happens here? Well, we've seen it many times now. Push RBP first to preserve that, and get a stable frame pointer here in RBP. So now in this function, now this is the top of the stack, and this is our part of the frame over here inside of the times 2 function. And then something similar happens, like we saw happen before. So EDI had the first int, so it's here, it's 5, and then GCC figured, well, we better put that into memory. So we get it into memory here at RBP -4. Then we have an actual L value, an actual thing we can look at in memory. Then it copies that back into EAX. And then it's going to multiply that value by 2. So now we have this thing here that we're going to multiply by 2. And even on O0, GCC figured, well, if you're just going to multiply by 2, it's going to be a lot faster to just add the number to itself. So I'll just do that for you, even at O0. So we get the instruction here, add EAX, which will add EAX to itself and leave the result also in EAX. So 5 plus 5 equals A. So we get A in our AX. Then we have to pop RBP, which is nice because we're going to return to our sum times 2 function, and we are going to expect to have our good old RBP here when we come back, right? So that we can keep executing and know where stuff is. And then we return. So we just jump back here to the next instruction after the call instruction. And then we are about to leave the sum times 2 function. And there are a few things to think about here. The first thing is we need to return this value. And we have seen before that RAX or EAX is the return register. So we're going to have to copy this value into EAX. But we just call a function, and the function will have returned that value into EAX. So since we're just returning whatever was returned to us, we can just leave it in there. So we don't need to do anything more. The A value is already here in EAX. Then there's a new instruction that we haven't seen before, which is the leave instruction. And the leave instruction is basically just a shortcut to, or a shorthand to restore the values of RSP and RBP. So it's doing two things. It's just one instruction. I'll visualize it in 2 steps. So the first thing it does is to copy RBP back into RSP. So we go back here. RSP is now pointing down here, but we have a copy of RBP here. So it will then copy RBP back in RSP. So now we have restored RSP. Okay, so when we get back to our or then we get RSP back as it was. The second thing we have to do is what we've always done, right? In every example so far, we have to pop RBP for the caller, so we don't mess up their RBP. So if we do that again, we popped RBP off the stack, restore the value of RBP, restore the value of RSP, and then we return control to whoever called us. All right, and again, that was quite a lot of stuff. So let's go back to Compile Explorer again and see if we can do optimizations here. Let's try O2. And this looks a lot nicer, I think. A lot less stuff going on. So if you first look at the times2 function, it used the LEA trick again. So times2 is going to just multiply the number by 2. So it decided to do that in one instruction, LEA, add the number to itself, and leave it in EAX. Right, so just like before, we can, with LEA, we can choose where to store the result, and we don't have to copy it in there after. So with one instruction, add the number to itself, leave it in the return register. And in sum times2, the first thing we have to do is to add the two arguments, which will be in EDI and ESIs. We'll do that first, and then we're supposed to call times2. But what you can see here, it just inlines the entire thing. So it's inlined all of times2 into sum times2. So it will then take RDI plus RDI, because we've now added these two together and they ended up here in EDI. Add those two together and put the result in EAX. So now we have multiplied the sum of these two arguments, and then we can return. And if we just go over here and we make this static, so it has internal linkage, then GCC just figures, well, I'm not going to even emit any code for that function. It's not in use, and no one else is going to be able to link to it. So we can just not emit code for it at all. And this entire example just collapses down to add one LEA and return. Okay. Yeah, then we are nearing the end here. And remember in the beginning, I promised you that all of that code we looked at in the beginning, we will be able to understand what it does and why it is the way it is. So I think we can have a look at that again and see if what I told you is true. Can we understand all of this stuff and why it's here? So let's look at this. It's a bit contrived and strange code, but it's just to be able to use all the stuff that we have learned so far. So we have this computer function. The computer function takes one int argument, int a, and also an unsigned int b. Then we have a for loop, which just decrements b. As long as b is larger than 0, we just go minus minus b. So we just decrement b until it reaches 0. And for each iteration, we just add b to a, and then we return a. Okay, so stupid function, but just does some stuff that's interesting to look at. So let's look at the computer function here. So all of this is then the assembly for the computer function. Let's see if we can actually understand why all of this stuff is here. So first, we're going to push RBP because we want to preserve RBP for whoever called us, which we talked about. Move RSP RBP so that we have a stable base pointer to our stack frame. Then we put the two arguments that we got in EDI and ESI, because those are the first two int arguments according to the calling convention. We put those in memory so that we have proper L values, proper variables that we can look at and take the address of and everything. And A is going to live at RBP minus 4, and the B parameter is going to live at RBP minus 8. And then we get to the loop, and it decided to implement that by first just an unconditional jump to L2. Which is here, and then we compare that to RBP minus 8. Yeah, so RBP minus 8 is now the B value, and we compare it to 0, and then we go jump if not equal. Well, if we're not at 0 yet, then we jump to L3, which is the beginning of the for loop. Otherwise, we take A here, put it into EAX, and then we pop, that's the return register, and then we pop RBP to restore it for our caller. And then I just have to check my Telegram here. Yep. Then in the caller function, it's going to call the computer function with the arguments 1 and 3. And then it's going to check if the result was less than 10. Then it's going to return that value. Otherwise, it's going to return 10. So it's just capping the result at 10. So again, we do the push RBP, move RBP RSP, which you've seen before. Set aside some stack space by subtracting 16 from the stack pointer. Put the arguments 3 and 1 into ESI and EDI. Call the computer function. Then we're going to get the result here in EAX. And we're going to store that in RBP -4. So that will be our I variable. And then if I is less than 10 was implemented here by comparing it to 9. So, and then do jump greater. So it's checking, is it greater than 9? If it's not greater than 9, we're going to fall through here. Put the value from memory here into the return register. And then we're going to have to do the conditional, and then on conditional jump to just jump to the end of the for of the if. If it was greater, we're going to jump to L6 and put 10 into the register instead. And then we just leave and return like we saw before. So I hope that I fulfilled my promise and that you now can understand every single line, not only what it does, but also why it's there. Yeah, and let's get back to the slides again. Yeah, so just some tips here at the end. You can hover over the instructions and then get like a summary of what each instruction does before, and then you can Google that if you don't learn enough from just hovering over the instruction. If you're going to use Compiler Explorer, first make a local standalone reproduction. So try to inline all your code. Maybe your IDE can help you, or just copy paste, get everything into one file that compiles by itself. That doesn't have a lot of includes of your other private header files and stuff like that. So when that compiles and just reduces as much as you can, and then paste it on Compiler Explorer, then you might be able to understand what's going on. It's really hard if it's too much code. Compiler Explorer has a bunch of libraries. So it has stuff like Boost, Catch2, FMT, Eigen, a bunch of useful libraries. So those you can actually use on the site. Use ints instead of complicated types. So this talk, I've just used ints, basically. Things get more complicated when you have more complicated types. But a lot of the things you're curious about can often be figured out just by using ints. And then when you've understood what's going on, then you can try to substitute in maybe your more complicated types. Yeah, and don't try it out on your full project. This is a really nice tool to understand. Like if you want the answer to one specific question, then you can ask it like, here's some little code. I want to figure out one particular thing. It's good for that. It's not good for figuring out what happens with your whole program. Yeah, so there's going to be a few questions now in here, and then we're going to move over to Zoom, where we can have a lot more questions and interesting discussion, hopefully. And those were some of my tips here at the end. So if you have any of your own tips, then I would also appreciate if you share that with me and the others. Yeah, and that's it. Then I am ready for some questions if you have any. All right, then we are going to move. Yep, then we are going straight to the Zoom chat. So I'll see you there in half a minute or so. And thank you for coming to the talk. And yeah, bye-bye.
Thank you very much, Anush. That was excellent. I look forward to catching up with you in the Zoom. But for anyone who can't join us there, we'll say goodbye. Thank you for your time.